In this video, I'd like to evaluate the indefinite integral of 1 over 5 plus the square root of 2x. Now, you may want to pause the video here for a minute or two and see if you could work through this problem, or at least get the problem started, and then maybe compare and contrast your solution with the one I'm about to work through. So at first glance, this integrand doesn't fit a familiar form. Nothing's really jumping out at me in terms of how to evaluate this integral. So with integration, sometimes it involves a little bit of trial and error. Definitely more so than taking derivatives. Taking derivatives, they may be algebraically complicated, but it's usually much more apparent what to do. And with integration, sometimes, as I said, it takes a little bit of possibly trying something to see if it works. Now, if all else fails, a U-substitution is always at least a good thing to consider. It's a very commonly used integration technique. So I'm going to start off by making a U-substitution here. Now, in terms of our candidates for U, well, nothing's really jumping out at me other than just letting the denominator be our choice for U. So let's say U is equal to 5 plus, well, the square root, I'm going to use the 1/2 power because we're going to have to take the derivative of U. So let's just write the square root of 2x as 2x to the 1/2 power. Same thing. So our du, the derivative of u, well, the derivative of 5 is 0, and the derivative of the square root of 2x, or 2x to the 1/2 power, we'll need to apply the chain rule. 2x, power comes out front, drops by 1, inside stays the same, and then we multiply by the derivative of the inside, which is 2, the derivative of 2x. So the 2 and the 1/2 cancel, so it looks like our du is 1 over 2x to the 1/2 power. Okay, so that doesn't, oh, don't forget the dx. So that doesn't look like it helps us much because when we make this first substitution, so we're going to plug this in. We're going to plug this in up here. So we'll get 1 over u. But the problem is the expression for du is containing this 1 over 2x to the 1/2, and that doesn't exist there in the integrand. So remember, with u substitution, all the x's have to be converted to u's, and the dx has to be converted to a du. So let's see if we could work with this before giving up. So let me just rewrite this. Let me just switch back to blue. Let me just rewrite this second line. So we have du is equal to 1 over 2x to the 1/2 dx. Well, if this is going to become u, well, we have to substitute for the dx. So let's solve for dx. If we multiply both sides here by 2x to the 1/2 power, then we'll get 2x to the 1/2 power times du is equal to dx. Well, we can't make this substitution because it's got an x and a u. So let's see if we could substitute in for this 2x to the 1/2. Well, we have an expression we could use up here. We have an equation we could use up here. So there's a 2x to the 1/2 in that equation, and if we subtract 5 from both sides, well, look at that. We'll get u minus 5 is equal to 2x to the 1/2 power. So now we could substitute in for this 2x to the 1/2 power. So we could replace that 2x to the 1/2 with the u minus 5. So we could say u minus 5 du is equal to dx. And now we have an equation that converts the dx to an expression containing only u and du. So this is going to be substituted into our integrand. Perfect. So now we've absorbed all the x's and dx's and we've replaced them with u's and du's. So let's make this substitution. We'll have 1 over u. So remember the denominator, the box in red is our u, so 1 over u. And then the dx becomes a u minus 5 du. This is a much easier integral to deal with. So this is u minus 5 over u du. And we could split this fraction up. So now, when we have two terms on the bottom, like in our original problem, we can't split up that fraction. But when we have a single term on the bottom, now we could split this up as u over u, which is 1, minus 5 over u du. Okay, now we're finally at a point where we can integrate. We can find the antiderivatives. So the antiderivative of 1 would be u, and the antiderivative of 5 over u, or 5 times 1 over u, well, that's the natural log. The antiderivative of 1 over u is the natural log of the absolute value of u. And then there's a 5 out front. So 5 times the natural log of the absolute value of u. And don't forget the plus c, the constant of integration. Okay, and so that's it. The integration is done. Now we just have to back substitute and replace the u back with what u is holding the place for. And u is equal to 5 plus the square root of 2x. So when we go back to x's, we'll have 5 plus the square root of 2x minus 5 times the natural log of the absolute value of 5 plus 2x square root plus c. Now the last thing to notice here is that we don't need those absolute value bars because the square root of 2x is always going to be non-negative. The smallest it could be is 0, so it's going to be either 0 or positive. So you're taking the number 5, you're taking a positive number plus something that's either 0 or positive. So inside the absolute value bars is always going to be positive, so we could drop them. In this case, they're not necessary. So 5 plus the square root of 2x minus 5 times the natural log of 5 plus the square root of 2x plus c. And that looks like it does it for this particular problem. So a couple of things just to recall. U-substitution is a good thing to try when you're not sure exactly what to do. It may not always work. Often it does. Also, as you can see from this example, sometimes the U-substitution isn't a one-step process. You can't just choose your value of u, find du, and make the substitution. Sometimes there's a little bit of algebraically moving things around to get what you need, but in this case it worked. All right, so that does it for this problem. I hope this was helpful.